If you're an engineer, then you need to understand turbulence. Welcome to Mr. CFD, your go-to experts in consulting, simulating and training for a wide range of CFD projects using ANSYS Fluent software. Our team specializes in providing top-notch services, including learning products, dedicated online training and comprehensive courses. We offer personalized consultation and handle complex CFD simulation projects to meet your specific needs. Mr. CFD offers professional advice on designing and optimizing different systems based on engineering principles and CFD simulations. Benefiting from Mr. CFD services decreases the project simulation time and cost dramatically. Your CFD projects will be investigated, simulated and trained with the highest quality and a reasonable price with our most reliable specialists in the shortest time possible. Contact Mr. CFD to prevent wasting your time and money. Mr. CFD experts will be in touch with you in the shortest time. Enjoy Mr. CFD technical support, Turbulence, a word that evokes images of swirling chaos, of unpredictable motion, of forces beyond our control. We see it in the sky, as clouds morph and churn. We hear it in the roar of a jet engine, or the crashing waves against a rocky shore. Turbulence is everywhere in the universe, from the smallest eddies in a stream to the vast cosmic jets spewing from black holes. In the world of engineering, turbulence presents a unique challenge. It is a fundamental aspect of fluid dynamics, influencing everything from the efficiency of airplane wings to the flow of blood in our arteries. Understanding and predicting turbulence is essential for designing safer, more efficient and more reliable systems. But turbulence is a fickle beast. It is chaotic and unpredictable, governed by complex equations that are difficult to solve even with the most powerful computers. This is where computational fluid dynamics, or CFD, comes in, a powerful tool that allows engineers to simulate fluid flow and study the complexities of turbulence in a virtual environment. Imagine a waterfall, a cascade of water plummeting over a cliff. As the water falls, it crashes and churns, breaking into smaller and smaller droplets. This is a visual analogy for the energy cascade in turbulent flow. Large eddies, the largest swirling structures in a turbulent flow, break down into smaller eddies, transferring energy from the large scale to the small scale. This process continues with each generation of eddies smaller and faster than the last, until the energy is dissipated as heat at the smallest scales, known as the Kolmogorov microscales. This energy cascade is a fundamental characteristic of turbulence, and it is one of the reasons why it is so challenging to simulate. To accurately capture the behavior of turbulent flow, we would need to resolve all the scales of motion from the largest eddies down to the smallest microscales. This is computationally very expensive, often requiring massive supercomputers and vast amounts of processing time. The sheer complexity of turbulence poses a significant challenge in the field of computational fluid dynamics. Direct numerical simulation, or DNS, the most accurate method for simulating turbulence, involves solving the Navier-Stokes equations, the fundamental equations governing fluid flow for all scales of motion. While DNS is incredibly powerful, it is also incredibly computationally expensive. It is like trying to simulate the entire Earth's atmosphere down to the smallest gust of wind. For most engineering applications, DNS is simply not feasible due to the immense computational resources required. To overcome this challenge, engineers and scientists have developed a range of turbulence models, which simplify the complex equations of fluid flow and make it possible to simulate turbulent flows on a more manageable scale. These models provide approximate solutions, capturing the essential features of turbulence while reducing the computational cost. One of the most widely used approaches for turbulence modeling is the Reynolds average Navier-Stokes, or Rance method. Instead of trying to resolve all the turbulent fluctuations directly, Rance models focus on simulating the mean flow behavior. Imagine a river flowing downstream. The water is constantly swirling and eddying. But if we average the flow over time, we get a smoother, more predictable picture of the overall flow pattern. This is the essence of the Rance approach. Rance models introduce additional equations known as turbulence closure models to represent the effects of the unresolved turbulent fluctuations on the mean flow. These closure models are based on empirical observations and theoretical considerations, and they provide a way to account for the energy cascade and other important features of turbulence without having to resolve all the details. Section 5, two equation models, KE and KO. Within the realm of Rance models, two equation models are among the most popular and widely used. These models use two additional transport equations to represent the turbulent kinetic energy, or K, and the rate at which this energy is dissipated, either epsilon or omega, hence the name two equation. The KE model, one of the most common turbulence models, is known for its robustness and computational efficiency. It has been widely used in a variety of engineering applications, from predicting flow over aircraft wings to simulating the flow in internal combustion engines. Another popular choice is the KO model, which offers advantages in near-wall regions where the flow is strongly influenced by the presence of the wall. The KO model is often preferred for simulations involving boundary layers, such as flow over ships' hulls or inside pipes. Section 6. Reynolds stress models, or RSM. While two equation models offer a good balance between accuracy and computational cost, they do have limitations. In flows with strong streamline curvature, swirl or anisotropy, where the turbulence intensity varies significantly in different directions, two equation models may not be sufficient to accurately capture the complexities of the flow. Reynolds stress models, as the name suggests, solve transport equations for all components of the Reynolds stress tensor, providing a more detailed and accurate representation of the turbulent flow field. RSM is particularly well suited for flows with strong anisotropy, swirl, or separation, where the turbulence is highly three-dimensional. However, this increased accuracy comes at a price. RSM simulations are significantly more computationally expensive than two equation models. They require more computational resources and longer simulation times, making them more challenging to implement and interpret. Section 7. Near-wall treatment. In many engineering applications, the flow behavior near walls is of critical importance. The thin layer of fluid adjacent to the wall, known as the boundary layer, plays a crucial role in determining skin friction, heat transfer and flow separation. Accurately modeling the near-wall region is essential for obtaining reliable CFD results. However, this presents a challenge because the flow in the boundary layer is characterized by steep gradients in velocity, temperature and turbulence properties. ANSYS Fluent, a leading CFD software package, offers a range of near-wall treatment approaches to address this challenge. Wall functions provide a simplified representation of the near-wall flow, while low Reynolds number models resolve the boundary layer in more detail, albeit at a higher computational cost. Section 8. Selecting the right turbulence model in ANSYS Fluent. With such a wide array of turbulence models available in ANSYS Fluent, selecting the most appropriate model for a given application can seem like a daunting task. The choice of turbulence model depends on a number of factors, including the flow physics, the desired accuracy, the available computational resources, and the project timeline. For flows with relatively simple geometries and flow patterns, such as flow in a straight pipe or over a flat plate, a simpler turbulence model like the KE model might be sufficient. However, for flows with more complex geometries, strong swirl or separation, a more advanced model like RSM might be necessary to accurately capture the flow physics. It is important to remember that there is no one-size-fits-all answer when it comes to turbulence modeling. The best approach is often to start with a simpler model and then gradually increase the complexity if necessary, carefully evaluating the results and making adjustments along the way. Section 9. Examples and applications. The applications of turbulence modeling in CFD are vast and varied, spanning a wide range of industries and disciplines. From aerospace engineering to biomedical research, from energy production to environmental science, Turbulence modeling plays a vital role in understanding and predicting the behavior of fluids in motion. In aerospace engineering, CFD simulations with turbulence models are used to design more efficient aircraft wings, reduce drag on fuselages, and predict the performance of jet engines. In the automotive industry, turbulence models help to optimize the aerodynamic design of cars, reducing fuel consumption and emissions. In biomedical research, CFD simulations with turbulence models are used to study blood flow in arteries, helping to understand the development of cardiovascular diseases and design better medical devices. In environmental science, turbulence models are used to predict the dispersion of pollutants in the atmosphere and oceans, providing valuable insights for environmental protection and management. Section 10. Conclusion: navigating the turbulent seas of CFD. Turbulence, with its inherent complexity and chaotic nature, presents a formidable challenge in the world of fluid dynamics. Yet it is this very complexity that makes turbulence so fascinating and so important to understand. Computational fluid dynamics, armed with a powerful arsenal of turbulence models, provides us with the tools to explore the turbulent seas of fluid flow, to unravel the mysteries of this ubiquitous phenomenon, and to design better, more efficient and more sustainable systems for the future. As we continue to push the boundaries of computational power and develop more sophisticated turbulence models, we move closer to unlocking the full potential of CFD, paving the way for groundbreaking discoveries and innovations in countless fields.